As he said, I'm Tom Newman. I'm at NASA Goddard. I spent the last 10 or so years working closely with Torsten Marcus to bring ICESat-2 onto orbit. While Torsten and I did lead the science side, Torsten as the project scientist and myself as his deputy, of course, there's a cast of thousands that all support these big missions and make them happen. And it really is a privilege and a pleasure to get to present this top level overview and how some of the data products work, because there's so many bits and pieces that go into it, and lots of trials and tribulations over the years. Okay, great. So let's go ahead and go forward by a slide. Awesome. So my goal in this presentation is to cover the basics of the measurement. The measurement is made by an instrument called ATLAS, the Advanced Topographic Laser Altimeter System. And now I'm seeing a white line on my screen. There we go. Yeah, so it's to cover the basics of the instrument, of the mission, and then we're going to get into the data products. And the data product that I'm going to talk about is called ATL-03. That's the level 2A product that supports all of the higher level products, such as the land ice product, ATL-06, and the sea ice products, ATL-7 and 10. And what you see on this figure is an outreach campaign that we had going last year, began right around when the last Hack Week started, of examples of ICESat-2 measurements from iconic places around the world, and we'll revisit a few of these as we go through. Let's go on to the next slide, please. So the objectives listed here on the slide have been our guiding objectives for the mission since we began. And not surprisingly, those objectives revolve around changes in the cryosphere, both the sea ice, changes in sea ice freeboard and sea ice thickness, as well as contributions of the polar ice sheets to global sea level. I'm not going to dwell on these, but happy to talk through objectives or requirements if anyone's interested at the end. Let's go on to the next slide, please. So the basic measurement concept of ICESat-2 is shown in the figure here. As all of you I'm sure know, ICESat-2 carries a LiDAR. That LiDAR is called ATLAS. And what it does is that instrument makes a range measurement. It sends out a little pulse of laser light and times how long it takes that laser light to go from the spacecraft down to the Earth and back again. And that's the key thing that ATLAS does. It transmits laser light and times that round trip time of flight. The two other pieces of information that we need are the position of the observatory in the orbit. So one could say whether you're over Greenbelt, Maryland or Greenland. And then the pointing angle. Are we pointed perfectly at nadir, a little to the left, a little to the right? And in ground processing, we tie those three pieces of information together: the round trip time of flight, the pointing angle, and the position of the observatory in space, to figure out what the elevation of the surface of the Earth is. What's the elevation where that laser light intersected with the surface of the Earth? Fundamentally, that's all that's going on. Of course, in detail, there's more pieces to the story, and we're going to go through a few of those in the next couple slides. Next slide, please. So if one could take a snapshot of the laser footprints on the ground, it would look similar to the figure over on the right. ATLAS generates 6 laser spots on the ground from a single pulse of laser light. So the laser generates a single pulse. On board, it's split 6 different ways, if I can get my fingers right. And they're laid on the ground in a little rectangle pattern. By slightly clocking the spacecraft, as it flies along its orbit, it describes 6 ground tracks on the surface of the Earth. You'll notice that 3 of those dots are darker green, 3 are lighter green, but both are green. The wavelength of the laser light is in the green part of the spectrum, 532 nanometers. And the darker green and lighter green indicate that there are some beams that are relatively stronger and some beams that are relatively weaker. The difference in energy between those beams is approximately a factor of 4. And we typically refer to those as the weak beams and the strong beams. Over on the left of the left-hand side of the figure are some specs on how those ground tracks are laid down on the surface of the Earth. The beams are arranged in pairs, 1 strong beam paired with 1 weak beam, and those beams are approximately 90 meters apart. The pairs of beams are spaced much wider in the across track direction, right around 3 kilometers. The transmit frequency of the laser is 10,000 times a second, or 10 kilohertz. And at our orbit altitude, that gives us a spot on the ground in each of those 6 spots every 70 centimeters along track. So under clear sky conditions, that means you get essentially continuous coverage in the along track direction. Of course, clouds will block visible light, like green laser light. But in clear sky conditions, you get these 6 tracks on the ground. The footprint size is another topic that comes up often. You'll see a few different numbers in here, and I apologize for that. The pre-launch required diameter was less than 17 meters. We've been analyzing on-orbit data now, and it seems likely it's right around 12.5 meters, so quite a bit smaller than the 17 figure there. And then the only other comment I was going to make here was on the detection side. So we've talked about a little bit about transmitting laser light. The approach we use on the detection side is called photon counting. So instead of digitizing the returning energy, what ATLAS does is it detects individual photons as they come into the telescope and into the electronics of the instrument, and times the arrival time of those photons. So we're able to send out really weak pulses of laser light and detect individual photons as they come back in. And it's those returning photons that are the basis of the elevation measurement that we're making in ISAT-2. Let's go on to the next slide, please. So the 2 big sides of ATLAS you can think of as the transmit side, where the light is generated and sent down to the Earth, and the receive side. This is a schematic showing the components in the transmit side. ATLAS, the Advanced Topographic Laser Altimeter System, carries 2 lasers, only one of which is on at any point in time. We turned on our laser in early October of 2018, and we continue to use that laser. So it's been over 1.5 years now on that primary laser transmitter. After exiting the laser, it goes through some combining optics. A little piece of the laser light is picked off in the laser sampling assembly, and that enables us to measure the start time of when that laser pulse leaves ATLAS. From there, the beam passes through a number of optics, a steering mirror, and then ultimately through a diffractive optical element that generates those 6 beams. So there's one laser generating one pulse of laser light that then is split 6 different ways as the light is leaving ATLAS. Let's go on to the next slide. And this is a similar block diagram on the receive side. In the lower right, you see the arrows indicating the returned laser light coming back to ATLAS into the telescope. The telescope focuses the light onto the focal plane where those returning photons and returning light are coupled into 6 individual fiber optics. Those fiber optics go through a filter assembly that only allows green wavelength light through. Our center wavelength is 532 nanometers, and the passband on these filters is really narrow, just plus or minus 15 picometers. And the reason for such a narrow passband is that the sun also puts out a lot of light in that part of the spectrum. So we want to do as well as we can and reject as much of those background photons as possible. From the filter assembly, the photons go into the detector, and our detectors are photomultiplier tubes. So individual photons enter the elements of that PMT and then get converted to an electrical signal, which we can then time the arrival of and keep track of and do various statistics on. So big picture, those are the components on the receive side of ATLAS. Let's go on to the next slide if we can. Cool, so after leaving the PMTs, we have a small electrical pulse. And maybe where I should start here is over on the left side, where you see the weak spots and the strong spots. For those weak spots, each one of those PMTs, there's 16 elements in the photomultiplier tube. And for the weak spots, we're grouping 4 of those elements together. So effectively, there are 4 channels for each weak spot. And that's indicated by the green elements in the middle figure top. Down below is how we separate and spread the light for the strong spots. For the strong spots, we're using each of those 16 detector elements individually. And so for the strong spots, each of those 16 elements support 1 independent timing channel. So there's 16 timing channels for a strong spot and 4 timing channels for a weak spot. Um, for ATL03 and for higher data products, you probably will never know or never care which timing channel a particular photon was detected on. We certainly keep track of that at the lower level data to make sure light is being evenly distributed and make sure the performance of ATLAS stays consistent through time. So we're continually monitoring how much light goes to which detector element and are looking for timing and ranging biases between those elements. So let's go on to the next slide, please. Great, so we're generating all these photon arrival times on board from transmitted and return ATLAS laser light, as well as from background light from the sun. Now, ATLAS detects so many photon events that we don't have the bandwidth to send the information for every one of those arrivals down to Earth. So what ATLAS does on board is it figures out through algorithms where the likely, where the surface returns likely are in time. So on the left, on the far left, there's a diagram of the atmospheric histogram that is used to support the atmospheric science data products. But what this histogrammer does is it just counts returning incoming photons, bins them into these 30-meter high bins, and combines it over 400 shots. And so it's not very precise determination of where the surface is, but it gives ATLAS a big picture of where are the locus of the most photon returns. In that middle figure, we have something we call an altimetric histogram, which is a much smaller histogram, which is what ATLAS is using to figure out where the surface return probably is. It uses the information from the altimetric histogram to set those telemetry bands on the far right. Now, those telemetry bands are the bands where we are transmitting all of that photon rate data to the ground for further processing. So from biggest to smallest, there's an atmospheric histogram that's 14.5 kilometers high. There's an altimetric histogram, the height of which is determined by the roughness of the surface of the Earth and where you are on the surface of the Earth, and then those telemetry bands. Now, when this system works well, you get a single telemetry band that contains the surface and some buffer of photons around that surface. When this system doesn't work well, we can, instead of getting the surface, we get the top of a cloud, for example. If you're over the middle of the tropics with a large storm system, none of that laser light is getting through to the ground and back again. And ATLAS says, oh, there's a strong return from this particular height, and it turns out to be a cloud top. And we'll see some examples of what that looks like as we go forward. But for clear sky conditions, the onboard software of ATLAS is doing very, very well at picking the surface out and sending the relevant photons. Let's go on by one slide, please. Lots of times folks ask for some of the technical details, so I'm not going to walk through all the rows in this table or the next table, but I believe you'll have this presentation open to you or available to you, so if you're curious about any of these numbers, they're here for your reference. You can also find most of these on our website. So that previous slide was details about the transmitter. This is details about the receiver. And I won't belabor that one any further. Okay, so data products. We get data downlink from the spacecraft about 7 times a day at ground stations in Svalbard and Poker Flat, Alaska. And networks, NASA networks bring the data from those locations to Goddard for processing. We're downlinking about 450 gigabits of data per day, which is under our requirement, which is great. The lowest level data product is ATL01, and that unpacks the data, converts it from binary, and stores it in HDF5 format. Unless you're really into the details of ATLAS, there's no reason to look at ATL01. I don't look at ATL01. ATL02 is the lowest level we think anyone could possibly be interested in. At the ATL02 level, we're applying conversions to turn those zeros and ones into times, temperatures, and voltages across ATLAS, and calculating the photon time of flight. So it's combining those transmit times and the photon receive times to figure out what that round trip time is. The data is organized by beam. There are those 6 different beams, 3 strong and 3 weak. And ATL02 also passes along spacecraft data that's used in the geolocation process. So information on the pointing angle of the observatory or data from the GPS are also within ATL02. Let's go on to the next one. Now, this one is the lowest level product we think scientists are going to use, and the data of downloads at NSIDC kind of bears this out. ATLO3 is the geolocated photon product. It contains a latitude, a longitude, and a height for every photon event for which Atlas telemetered information to the ground. We use those three pieces we talked about at the beginning: the position of the observatory in space, the pointing angles for the Atlas laser beams, and then the photon time of flight. Combining those three things together, we calculate what the photon ground bounce point is, and thereby determine what the elevation of those photons are in a particular reference frame. All of the ISAT-2 elevations are referenced to the WGS-84 ellipsoid, making it really easy to compare ISAT-2 elevations with, say, GPS elevations. One thing that may or may not matter to anyone is that we're only absolutely geolocating one photon every 20 meters and then locating the other photons relative to it. And that was mostly to save on computational efficiency. It turns out to be computationally really expensive to do that first geolocation step. But since we know very accurately where each photon is relative to each other, we can very quickly geolocate the other photons within a particular segment. This 20-meter segment we call the along track geolocation segment, and those photons that are precisely geolocated we call reference photons. This 20-meter posting interval or 20-meter segment interval comes back again in several of the other data products. So in case anyone is interested where that 20-meter choice comes from, it comes from ATLO3, and it's an outcome of our particular geolocation strategy we're using on the photons. Let's go on to the next slide. So what does this data look like? You get a figure such as you see here. In that top figure, we have meters above sea level on the y-axis, time along track on the x-axis, and each one of those little dots is a photon that Atlas detected and telemetered data for. You can see the background photons up above the surface. It's sort of that pink cloud-looking thing, or a haze, I guess, of dots. But the surface return jumps right out to your eye. That's that heavy red line. It's composed of thousands and thousands of individual photon returns that cuts across the scene from left to right. This particular scene is going from roughly sea level up onto the edge of the ice sheet. I believe this is in Greenland. And yeah, so the problem for higher level products becomes, how do we determine the surface out of that photon cloud? ATLO3 takes a first shot at that by classifying photons. ATLO3 has a histogram-based strategy to do a discrimination of which bin vertically has the most photons and therefore is most likely to contain signal. There's a photon rate parameter on ATLO3 for the signal confidence level of each photon, and they're classified as very high or high likelihood of being signal, medium or low likelihood of being signal, and then finally noise or background, those photons that we think there's no way that they're signal. So what you get out of ATLO3, if you plot the classified photons, is you go from that top figure down to that bottom figure. By and large, ATLO3 and that histogramming approach does a good job of pulling the signal out of the noise. Higher level data products then take these likely signal photons and do other stuff to them. That's a technical term, to figure out exactly what the surface height is along track. And you'll hear about that from Ben for land ice and whoever is presenting the CIS data products today. Okay, let's go on to the next slide, please. We do get questions about geophysical corrections, about what's being applied on ATLO3 and what isn't. Here's a handy go-to table. The different corrections are here in the first column, the input parameters that we use, the output parameters that come out of that part of the algorithm, and whether a value is applied as a reference value indicated by the R, or whether it's a correction applied on the product. Naturally, we went back and forth quite a lot with the science team and the higher level data product leads to select these and to apply them in an easy way. The values for each of these are contained within the ATLO3 product, and they're posted at that 20-meter along track cadence. So if, for example, you didn't like the solid earth tide model that we applied, it is easy to undo that by subtracting it off and then using your own preferred solid earth tide. That was one of the concepts of how we set this product up. Some of the higher level products aren't interested in using ellipsoidal height. They may want to use an orthometric height. So there are parameters on here that allow those algorithms to work really efficiently to convert the reference frame, if you will, of the ellipsoidal heights to something else. The details on all of this stuff is in the what we call the ATBD. That's the algorithm theoretical basis document. Each one of the products have one of those, and that tells you in detail from beginning to end what happens in the processing of that product and how is each parameter generated. Naturally, they're kind of involved, but they're all publicly available, and you can go in and read about our thought process and how each one of these steps is implemented. On the next slide is the flow chart of how ATL03 gets generated. And I won't belabor all of this. You can refer to it at any time you like. Suffice to say, in the upper left, we have photon times of flight, the precision pointing determination of each of those atlas vectors, precision orbit determination of where we are in the orbit, and those get combined together to do an initial geolocation, followed by a photon classification of what's signal versus noise, and then flowing to a final geolocation that then ends up on the ATL03 data product. Happy to talk through any of these boxes in as much detail as folks like, and there are references in here to the different sections of the ATL03 ATBD. So when you can't sleep at night and you're wondering exactly how does the photon classification work, you can go to section 5 and read all about it. Let's go on to the next slide. So I always like this figure. This was our first light figure from October 3rd, 2018. We launched on September 15th, 2018. And this was the first figure that Torsten and I got in our email very, very early in the morning of October 3rd. The Atlas laser got turned on October 1st, so we knew the data processing team was working on generating this first look at photon heights from space. And I didn't sleep particularly well that night because I knew it was going to show up at some point, and I think it was about 3 or 4 in the morning that it came in the email. And super exciting for me to see a big that we see the surface, the concept works, and we can telemeter the data that we want to the ground. Once those photon times and locations and pointing angles are all on the ground, we know what to do with them from there, and we know how to iterate to make these locations better and better. But this was a super exciting figure for me, so I do like to share it. Let's go on to the next one. The data in ATL03 is massive. It's way too big to have a single revolution around the Earth to be a data product granule. So we've broken the product up into 14 individual regions. Region 1 starts off at the equator heading northward, wrapping all the way around until region 14 is the part of the Earth where the spacecraft is just approaching the equator again. So each one of those revolutions has 14 different regions, and we try to choose them intelligently. So if you were interested in interior Antarctica, you could just pull region 11 and you'd get the region that you want. Let's go on to the next one, which talks about the orbit and our coverage. From our 500-kilometer altitude, the spacecraft covers from 88 degrees south to 88 degrees north. It makes 15 revolutions around the Earth every day. And that orbit repeats every 91 days. If you do the math on that, you'll find out that there's 1,387 unique ground tracks. And for each one of those ground tracks, there are the 6 individual beams draped around it. We often call that ground track the reference ground track, and it's the imaginary line down the middle of the beam pairs. But that RGT number that goes from 1 to 1387 is a useful way to communicate to us or to your peers about which track are you looking at and which region are you looking at. And that's a quick way to clue somebody in as to where you're seeing something interesting or perhaps seeing a problem. You can download those ground tracks at the website right there. They're posted as KMLs. Let's go on to the next slide. In the polar regions, we're pointing at the same ground tracks every 91 days with the goal of measuring elevation change of the ice sheets and measuring the sea ice freeboard. In the mid-latitudes, our requirement is to enable estimates of global canopy height as a means to get at above ground biomass. And so we do this series of off points in the mid-latitudes, where every 91 days, instead of pointing exactly where we did the first time, we point a little bit off to the left or a little bit off to the right. And you get a pattern like you see here. The heavy blue lines are where we would point on, say, the first pass on this particular reference ground track. The second time passing over that area 91 days later, we aim to split the difference, if you will, between the adjacent ground tracks. Similarly, the next time around, 91 days later, we again try to split that difference so that over time, over the first 2 years of the mission, we generate a denser and denser and denser ground track coverage. Ground track coverage doesn't necessarily equal data coverage, particularly in the mid-latitudes. It's often cloudy. Although I'm looking out my window here in Maryland today, and it is a nice day for altimetry out there, but such is not always the case everywhere. Let's go on to the next slide. There's some interesting things that you can end up doing with this orbit. A few of the stats there again, but whereas the first ISAT mission, which I haven't talked about a whole lot, was just a single beam LiDAR, and at crossover locations, you'd have a single beam crossing a single beam, and you could measure height change that way just by comparing those two. With ISAT-2, we have 6 beams crossing 6 beams. So anytime a reference ground track intersects another reference ground track, you have 36 individual crossovers that you can use to either assess instrument performance or exploit it for science. These crossovers happen all around the world at all sorts of different time latencies. One of the ways we keep track of ATLAS and its performance is to look at crossovers that occur within 24 hours of one another in Antarctica. So Antarctica changes slowly. If you have track A and track B that are crossing just 6 hours apart, ISAT-2 should be giving you a consistent set of measurements from pass A and pass B. Of course, you can manipulate the time difference between crossovers you're looking at to start to get at interesting science questions. For example, precipitation. You can watch it snow in Greenland by comparing track A and track B and look for those crossovers that are separated by a week or 2 weeks or whatever your time period of interest is. So let's go on to the next slide, please. Here's the whole suite of data products and how they flow from each other. I've mostly been talking about ATL-03, which is in that top row there. The atmospheric data products, ATL-04 and 09, are over to the right. And those products together, ATL-03 and ATL-09, support each of those blue boxes. Those blue boxes are the surface-specific higher level products, where if I can pick on Ben, he takes the ATL-03 and ATL-09 and figures out how to define the ice sheet surface height as accurately as possible in an along track sense in ATL-06, and then those higher gridded products follow from there for each of them. The reason we have surface-specific products is that if you're looking for canopy height, you're probably going to handle those photons differently than if you're looking for ice sheet height. If you're looking for sea ice elevation and sea ice freeboard, you'll probably do something different than if you're looking for reservoir heights or river stage. All the along track products are currently at NSIDC, as many of you know, and some of the gridded products as well. We continue to bring more and more of them online as time goes by. Let's go down to the next slide. I won't belabor this slide either. Suffice to say that the data product leads and the products that they work on are shown in the table here. The low-level products were all led by folks within the mission at Goddard. And Torsten and I decided early on that the higher-level products, we would do well to take advantage of the scientific expertise in the community. So we worked to identify those data product leads for sea ice, for ice sheets, and so on. Let's go on to the next slide. I've just a couple slides on calibration activities. As we've alluded to, or as I mentioned earlier, all the ground tracks converge at 88 north, which is middle of the Arctic Ocean, and 88 south, which is in the middle of Antarctica. Turns out it's much easier to get to the middle of Antarctica. Dr. Kelly Brunt is our post-launch calibration lead, and she's been down at the 88 south line of latitude on 3 separate trips to date to measure the surface height of the ice sheet using GPS. Now, those GPS-based data sets provide an independent comparison for what ISAT-2 is measuring from space. And I've just put a screenshot of the table in here of a paper that Kelly led with Ben and myself supporting, comparing GPS data with the available ATL-03 data and ATL-06 data. And you can see the resulting bias and precision estimates, as well as the number of intersections that we looked at. Let's go on to the next slide, please. Yeah, I think this is a movie. I'm not sure if it's going to play or not. We'll give it a shot. This is the platform that Kelly and others use when down in Antarctica. Maybe that didn't work. We can go back by 2. And I can just point out the main features here. We're using ground vehicles to drive along several hundred kilometers of the 88 south line of latitude. That is one single long continuous sled. It's about 60 feet long. It's sturdy enough that you can leave your tent pitched right on the sled. And at the far end, the tail end of the sled, you see the little mast sticking up with the GPS antenna sitting on the top. Each one of the platforms has one of those with it, so we're able to take 2 independent measurements of the ice sheet elevation height and then cross that with the data from space. Let's go on to the next slide. The other thing we've done is leave out corner cube retroreflectors. And these are little pieces of glass about the size of the tip of your finger that reflect the incoming laser light. They're optimized to reflect light at that 532 nanometer part of the wavelength. And it turns out that you can detect these in the space-based data. Over on the upper right-hand is a figure of photon data from ATL03 over one of these corner cubes. And what you see is the green and then the blue and then the green is the ground return. And at the same time, you see all of these little red dots that are higher than the surface at exactly the height that the corner cube was placed. So that allows us to get a check on our geolocation. We surveyed in the location of each one of those cubes, and we can compare the latitude, longitude, and elevation, but especially the latitude and longitude of those cubes between the ISAT-2 data and our ground-based GPS data. Let's go on to the next slide if we can. As many of you know, data are publicly available. We'll see a lot in the next couple of days about how to access that data. As Torsten said, they've done a really good job of making data access easy as we can make it. The challenge often, especially with ATL03, is in the data volume and making sure you get what you want. Over the first year, you can see some of the stats on data download there. It's really gratifying and satisfying to see so many different users using this data for all kinds of cool applications, some of which we didn't really dream of ahead of time, and really making the most of the data. Let's go on to the next slide. And I promise, Axel, I'm just about done. Lots of folks ask how Atlas is doing now that it's been on orbit for a year and a half. In that first year and a half, we've had one safe hold event, or as some people call it, Atlas's summer vacation. It took kind of 2 weeks off. And there were 2 Atlas software upsets back in November and another one in December. But otherwise, knock on wood, Atlas is really doing well. The laser energy graph is over in the right, and that's a really zoomed in figure. So although you see it's got a slope to it, the laser transmit energy is within 2.5% of the pre-launch value. Reminding you that we have 2 lasers on board. We've been using a single laser for the first year and a half of the mission. And we're currently running that laser at energy level 4. Naturally enough, people with a sense of humor chose the laser to have 11 different energy levels, because if you set your energy level at 10, where do you go from there? These go to 11. So right now we're at 4. We've only dropped by 2.5%. And the laser energy level steps are approximately 10% differences within each of those steps. So at some point we may need to move up to level 5 to get back to the transmit energy level we had at the beginning. The other figure on the left is a graph of the decrease in available fuel for orbit keeping. At 500 kilometers altitude, we do a drag makeup maneuver approximately once a week, sometimes once every other week, to stay in that same orbit. And over the first year and a half, I swear there is a slope to those curves, but it's pretty gradual, and fuel is not likely to be a limiting factor for us. And yeah, this one I think is my last slide. ISAT-2 is well on its way to meeting its science requirements and enabling all sorts of science discoveries that we didn't really think of ahead of time. So far, there's been now over 600 billion laser shots. Atlas is doing great. It's knock on wood. It's stable, it's healthy, it's doing its thing. And the data quality really looked fantastic. The table from Kelly's paper, we're suggesting that individual photon heights or aggregates of photons are good to about 10 centimeters vertically, and in geolocation space, latitude, longitude space, the locations are good to about 10 meters horizontally. those higher level products aggregate photons and apply various corrections, excuse me, and get that precision down even more. And I imagine Ben will talk about that some. The current data release is release 3, and it covers data from when we started collecting science data in mid-October up through April 6th, and there is more data on the way. We've been processing it in approximately 1 month long chunks, and this next chunk of data will bring us up through May 13th. We're currently evaluating that data now. Cool, Axel, that's what I have.
All right, thank you very much, Tom. That was wonderful. What a comprehensive overview over ISAT2. Thanks for working in the Spinal Tap reference. For those who didn't get that, some of the younger people may not be aware of that movie. Watch that movie, that's homework. A little program note. We're gonna do a 5-minute break here now and come back at 11:52. That is Pacific time. You have to do your own translation here. My calculations are not fast enough. And then Ben Smith is going to give us about a half-hour overview of some of the data products, specific data products. And then Anthony is going to come back and talk a little bit about revised schedules and where we are on that. I want to be alert people that some of you are in time zones where you're about to do other things, but watch Zoom channels. All of that information about schedule changes will be posted on Slack, so watch that. Things are in flux, so please be aware of that. So let's come back in 5 minutes. Let's turn it up to 12 now for Ben Smith, who is going to be telling us, introducing the sea ice product. Ben is the project lead for the land ice products, or the glacial products.
Thanks, Axel. I'm going to share my screen here. Let's see, there we go. So I'm going to be talking about ISAT2 data products, and I'm going to take us from the ATL03, which is more or less where Tom left us, and do kind of a whirlwind tour of all of the higher level products. I'm a land ice guy from way back, and so my understanding of things is sort of a little bit land ice centric, and so I hope I don't give too much of a short shrift to the sea ice and atmospheric products. But my main goal here was just to give you a quick look at everything that you might be interested in seeing in the world of products, and you can pick the ones as we go forward which are most relevant to the problem that you're addressing. Before I get there, I'm going to talk about some information that's common to all of the data products, including the timeline of data acquisition. I'll talk about the beams and spots and the orbital segments and how those combine to form file names, which is always a quick way of looking at the data product and figuring out where you're looking and what it's possibly showing you. So I'm going to start off by stealing a slide from Tom, which is a picture of the ISAT2 orbits on the ground. ISAT2 makes 15 measurements, makes 15 revolutions per day on the way to completing its 1,387 ground tracks every 91 days. So every time ISAT2 revisits all of these ground tracks, that constitutes one cycle of data. So every 91 days, we see a new cycle of ISAT2 data. And the reason for having these 1,387 reference ground tracks is that so we can be sure that ISAT2 repeats the same measurements every 91 days. This is most relevant for the ice sheets, where ISAT2 is trying to point at the same tracks every time, with the idea that if you go and measure the same track over and over again, you can see what's changed between those two measurements. So we should be making quarterly measurements of each track as we go around the Earth. And the repeat track numbers tell you which track you're revisiting for each different cycle. So again, a cycle is something that happens every 3 months, and that's the number of times, the cycle counts up the number of times you've revisited a particular ground track. So cycle 1 began shortly after ISAT-2 launched, September 15th of 2018. And then we've counted off a total of 7 cycles since then. The first data appeared a little ways into cycle 1. So that was October 14th of 2018. But there was a hiatus where we had to figure out exactly where the spacecraft was pointing after the instrument turned on. So it took us until roughly April of 2019 to get the satellite pointing exactly on the repeat tracks. So cycles 1 and cycle 2, while we would have liked them to be making repeat measurements, were making something kind of like repeat measurements. So if you look for repeat measurements of cycle 1 and cycle 2, they're not going to be quite where you want them. Cycle 3, we got everything worked out. We understood the software that was operating on the satellite. We understood the software that was operating on the ground. And from then on, we've been really tightly locked in on those repeat tracks. So ISAT-2 is measuring the same points on the ground with a repeat accuracy of sometimes like 6 or 7 meters. And you can, if you find the same data with the same repeat track measurement and you're in the polar regions, you can see very exact repeat measurements. Now, as Tom moving forward in time, as Tom mentioned, on June 26th of 2019, we had an instrument anomaly. We had one of the potentiometers that measured where the solar array was pointing give a value that we weren't expecting to get, and the satellite took a couple weeks vacation. When it turned back on, it was effectively in the wrong time zone. So it was using the wrong number of leap seconds, and it wasn't measuring the ground quite the way we expected it to be. So we had a few weeks of data that weren't as accurate as the other data that we've been collecting, and we elected not to release those data. So there's a period between June 26th and July 26th where everything was getting sorted out and coming back to nominal. And then from then on, we have good data right up to the present. So we have non-repeat data available in the very early part of the mission. We have repeat track mode data available from the first quarter of 2019 onwards with this one data gap. And so when you're looking at the data for your particular region, you may find all of these features appear in the data. Now, again, following on some of the stuff that Tom talked about, ISAT-2 measures 6 ground tracks, measures a nadir track, which is directly under the satellite, but it measures one track 3 kilometers to the left and 3 kilometers to the right of that. We call these pair tracks because each is measured by a pair of beams. It's measured by one strong beam and one weak beam. So with these, there's the wide spacing between the pairs, and then there's narrow spacing within the pairs where we're measuring 2 measurements that are separated by about 90 meters. The idea of this fine separation within the pairs is to be able to make accurate measurements of surface slope, which lets the ice sheet people correct their measurements down to exactly the same point every time. And know if the surface slope has changed, and also to do some comparison between the beams to make sure that we're getting consistent measurements between the 2 beams. Now, in all the data products, we refer to the pair tracks as 1, 2, and 3, and within the pair tracks, we refer to the individual beams as left and right. So we talk about GT1L, that's the left beam in pair track 1, or GT3R is the right beam in pair track 3. In this plot, we're showing the weak beams on the left and the strong beams on the right. Just to make things a little more interesting, we change that up. I'll talk about that in the next slide. This concept of repeating the same tracks over and over again lets us define coordinate system that follows the tracks around the world. So we can just count off distance along the ground track to form an along track coordinate that starts at the equator, goes north over the North Pole, then back around the backside of the planet, and then north again from the South Pole going north. And so all the products contain an x-ATC, and a long track coordinate that tracks from the equator all the way around the Earth and back to the equator. So it's roughly 40,000 kilometers for the complete orbit. But if you follow one particular track around, you start out at 0 at the equator, you encounter Greenland somewhere around 6,500 kilometers, cross the North Pole around 10,000 kilometers, get back to Greenland around 13,000 kilometers, hit northern Antarctica around 27,000 kilometers, and then get back to the equator at 40,000 kilometers. So these numbers are big. They're stored in meters, which makes them a little bit hard to look at. But the combination of which track you're looking at and your along track coordinate can tell you exactly where you are on the Earth. There's also the across track coordinate, which is just defined as being perpendicular to the along track coordinate. And that runs from plus 3,200 meters for GT1, so pair track 1. The center pair is right around 0, and the right-hand pair is at minus 3,200 kilometers. The way these coordinates are defined just defines a right-handed coordinate system with the x-axis following the reference ground track and the z-axis pointing up. So that leaves the y-axis pointing to the left. And again, when you're looking at a particular product, hopefully this isn't too confusing. So as I mentioned, to make things more interesting, ISAT-2 has to rotate 180 degrees a couple of times a year to make sure it has enough light on its solar arrays. So depending on what time of the year you're looking at the product, you may find the weak beams on the left-hand side of each pair, or you may find them on the right-hand side of each pair. So if we're in our forward orientation, you see the weak beams on the left. If you're in the backwards orientation, the weak beams are on the right and the strong beams are on the left. There are metadata fields in all the products that tell you what orientation you're in. And there are metadata fields on any product that gives you a particular beam that tells you what beam you're looking at. If you're interested in what piece of hardware is receiving and transmitting the beam, we designate those by spot numbers. So again, every product tells you what spot you're looking at. And so if you see something weird about a particular spot and you feel like you need to trace that to what piece of hardware you're looking at, you look at spot numbers which go 1 through 6, and this diagram tells you which spot is which. Repeating Tom's description of the different subregions for each product. When you combine subregions with the date and time information, you can figure out you can look at a file name for any particular product and you can figure out where you are. So each granule that comes from NSIDC, so each file that you might get containing ISAT-2 data, will tell you the product name. It will give you a long string that tells you when that was collected. This is the start of the product. So 2019, September 16, and then the time. The first number you'll see after the year, date, and time is the reference ground track. Then there's a number for the cycle, and there's a number for the region. So these 3 strings tell you which ground track it was, what number of times that's been collected, and what region you're looking at. And then the last 2 pieces of information are the data release and the version. Anything you order from NSIDC now will have release 3, and almost all of them will be version 1, although every once in a while you see a version 2 where something had to be corrected on the product. So people who are experienced with ISAT-2 can look at one of these product names, and they'll quickly pick out the date that it was collected and what reference ground track and what region it is, and then the cycle number. So all these things are ways that you can sanity check making sure that a granule of data that you have is where you think it should be. So with those sort of general considerations under our belts, I want to take a look at all of some of the products that ISAT2 has been putting out. So again, this is a chart that I copied from NSIDC that Tom also used. It shows the very high level data, the very low level data products that hopefully nobody will ever have to look at outside of the product office. But then those get turned into ATL03, which is probably the first useful product for looking at surface, land ice surface or ice sheet surfaces. ATL03 then gets turned into these higher level products. I'm going to talk about the land ice products, which is the leftmost column of data. I'll talk a little bit about the sea ice products, and then I'm going to touch on land and vegetation elevation and ATL09, which is the atmospheric product. So I'm going to go through these one at a time. Again, I know most about the land ice products. I've asked the sea ice people for some quick looks at the sea ice products, and then I'll just touch briefly on these other two products that might turn out to be useful. So the first product that I think people might need to look at is ATL03, the geolocated photons. This is the big one. It's a huge product that contains an amazing amount of information. The main things that I think people will be interested in looking at are latitude and longitude and elevation. But the other thing that you might miss on a first glance is the photon classifications, which tell you what an algorithm that's specific to each surface type thinks might be the surface out of all of those noise photons. Elsewhere in the product, you'll be able to find tide and atmospheric corrections, and you'll be able to find out a lot of parameters that are relevant for defining the configuration of the instrument. The advantage of this one is that everything is there. Every photon that Atlas has provided to us is stored in this product, and every parameter that you might need to know about that photon is there too. The disadvantages are same as the advantages. It's easy to get lost dealing with this product, and it's can be kind of cumbersome to work with. So downloading the data, getting it up on screen can all be hard. And we'll try and give you some tools to do this, but it's something that can take a lot of work. You can use it if you want to understand where the other products come from. You want to look at surfaces at a scale that's not well resolved in the higher level products. And if you have lots of storage space and lots of time to do it. So a quick look at this. This is one particularly hairy granule that shows you big vertical clouds of photons around the surface. It shows you the photons that are classified as belonging to the surface, but it also shows you places where ISAT2 Atlas locked onto something that wasn't the surface. It also shows you a place where a collection of photons that define the impulse response of the system came into the surface data frame. So it's all here, but you have to pick it apart by yourself. But some cool things that you can see if you take the trouble to look at it. This is a plot from a published paper showing that you can see land, trees at the coast, and even bathymetry of the ocean underneath the surface. You can see ocean waves, all mixed in with a generous helping of background photons. If you look at ice sheets, you can see, for example, in this case, this is a transit across a crevasse field in West Antarctica. So showing smooth ice sheet surface, showing some big rifty features with maybe some accumulation features created by those rifts, and then fine scale crevasses alongside that. So if you want to zoom in and see all the details of the surface, this is the way that you do it. A product that's near and dear to my heart is ATL06, the land ice height product. This is lots of little lines that have been drawn on top of the ATL03 product. What it gives you are surface heights. So it takes 40-meter line segments and fits those to collections of ATLO3 photons. So it gives you the height and slope of those segments. It gives you error estimates for how well that fit worked. It gives you tides and instrumental corrections and quality parameters that tell you how well the fittings worked. The advantage of this is that it's a lighter product than ATLO3. So instead of having to download every photon, you just download these estimates of where the surface height actually is. It gives you surface heights, where ATLO3 just told you how high the photons were. Now we're telling you how high we actually think the surface is. And it gives repeatable parameters. So it corrects for anything that might be different about the segments from repeat to repeat. So it tries to correct for any biases that might come out because the surface was brighter, or the surface was rougher from one cycle to the next. So it gives you something that we hope can be repeated and compared at sort of the centimeter level. The disadvantages of this is that the 40-meter resolution is too coarse for some applications. It doesn't do a great job in crevasses. It doesn't do a great job on bare rock. And the other disadvantage is that 40-meter resolution is too fine for some large-scale studies. So if you try and put an entire cycle of this data up on your screen at the same time, at least every computer I have access to will grind to a halt. So you use it if you want to make large-scale repeatable measurements of glaciers, or if you just want to see what a glacier looks like without downloading the whole ATLO3 product. So here's an example of this. It's showing the line segments fit to collections of ATLO3 photons. This has a pretty drastic vertical exaggeration. So these segments look like they have big slopes. I think if you zoom this out, this is a surface that is very, very, very close to being perfectly flat. Here's an animation showing what happens if you map all of the ATLO6 elevations for 4 cycles of data in Antarctica. It shows that we're pretty close to having wall-to-wall coverage of Antarctica. The same thing you can do for Greenland, except that Greenland's a little smaller compared to the dots, so it looks a little bit gappier. But this product has very good coverage of the 2 ice sheets. Now you can run into trouble with ATLO6 if you're looking at if the assumptions that were used to generate it are violated. This is an image that Philip Arndt came up with for a melt lake in Greenland. You can see that there's a water surface and a lake bottom surface. ATLO6 got confused because it only expects to see one surface over ice sheets. So when it was reporting heights, sometimes it picked the bottom, sometimes it picked the top. This is something that needs to be sorted out. Hopefully it will in a later release of ATLO6, but for now, you need different products to really see strange cases like this. ATL11 is a product that's shortly going to come out, giving land ice H of T. So the idea is that this gives you the potential to see changing surface heights by correcting out all of the topography that's defined by the repeat track measurements of ISAT2. It fits a surface to the ATLO6 measurements and boils out the cross-track variation in surface heights. This also contains quality and error assessments. It brings together multiple repeats of ATLO6, removes the signals that hopefully you're not interested in, and gives you a smaller, easier to use product that has the repeat track measurements built into it. The disadvantages are the loss of detail relative to ATLO6, and it may not work as well over very complex surfaces. And of course, the main disadvantage is it's not released yet. We expect to have this out sometime this summer. You can use this one to measure large-scale glacier change. So a quick look at this. This is a couple of 3 repeats over the edge of Thwaites Glacier in Antarctica, showing a smooth ice sheet profile with the 2 repeats lying nearly on top of each other. And then you get out onto icebergs past the coast, and you can see that different repeats have different heights of icebergs at different times. If you subtract out the first measurement of this profile, you can see that there are different heights for cycles 3, 4, and 5, and you can actually measure the elevation change by looking at the height differences between the 2 of them. And then out on the water, things get really scattered up, partially because of tides and partially because icebergs have been moving around. This is a product that you can use to map elevation changes. So these are height differences in Greenland, showing the drastic surface elevation drop that happened because of the big melt events that we had in the summer of 2019, and then partial recoveries of that over time afterwards, going all the way up into the middle of the early part of 2020. ATL 14 and 15, I'm not going to say too much about this. We will eventually have a gridded product for land ice. You can use this one if you're living in the future. It's not here yet. One last thing about measuring elevations over complex surfaces that I think it's important to point out. We also have a vegetation product that attempts to measure the height of trees in addition to measuring the height of the surface. This gives us a chance to do alternate surface detection methods. And it gives you an alternate photon classification compared to ATL06. And this one does, in some cases, do a better job of defining the heights of lake bottoms and lake tops. And in some cases, it gives you a better look at crevasse heights. So in some cases, if you're starting out to look at the data and you find that ATL06 isn't doing it for you, it might be worth taking a look at ATL08. I've got a good example also from Philip that shows ATL08 working well where ATL06 fell down for measuring the depths of a lake on Greenland. So in a lot of cases, it's worth looking at this if you're interested in understanding a different way of mapping photon heights into surface heights. Next, we're moving into the sea ice products. I sort of crowdsourced this off to the sea ice group to provide some slides. So I'm going to read what they told me. ATL07 is the basic measurement for sea ice height. It provides a long track sea ice surface and sea ice height and type. It puts together 150 photons, so it's measuring locations at, it's measuring at variable resolution in contrast to the land ice products that measure at a fixed horizontal resolution. So the advantages of this allows it to give you finer scale measurements where there are a lot of photons coming back, while extending the size of the window if it needs to put together more photons to map, for example, the height of a lead where there are fewer photons coming from a less reflective surface. It includes a lot of surface statistics, and again, it's a lighter product than ATL03. The disadvantages is that it's not calculated when the sea ice concentration is low, so less than 15%. It can lose resolution of small scale features, and you have to weight the height statistics by the variable segment lengths. So it's something to keep in mind when you're just adding up these heights, that it's not measuring at a fixed resolution. This is a good one to use for any kind of sea ice study. It's a great product and it's validated out very well. ATL10 takes the ATL07 freeboard and the ATL07 heights and turns those into a freeboard by subtracting the sea surface height measurements from the top of the snow surfaces. So it gives you 10 kilometer segments of the difference between the sea surface and the top of the ice. The advantages of this are relatively high spatial resolution and wide coverage. It's only provided where the sea ice concentration is greater than 50%, and it's not provided right up to the coast. And the freeboard near the ice edge may be affected by sea state somewhat. So it's important to know whether you're looking in the middle of the ice or towards the coast. This is one to use if you're doing Arctic-wide studies and you're focused on consolidated ice regions and you want to calculate sea ice thickness. So here are a couple of pictures showing ATL07 and ATL10. The top one, we have the photons, then the ATL07 segment height fit to those photons. And we have one spot where the ATL07 algorithm identified a lead where you're seeing through a crack in the ice down to the sea surface height itself. And then ATL10 took that estimate of where the sea surface height was and subtracted it from the on ice elevations to define the freeboard anchored at that one point to the sea surface height. So that would potentially let you make some estimates of how thick the ice was. The last products I'm going to talk about are ATL04 and 09, the calibrated backscatter and atmospheric characteristics. I'm calling these cloudograms because they let you look at what the atmospheric channel of ICESat showed. So these together provide profiles of atmospheric backscatter. They provide layer heights and optical properties. The advantages of these is that they show global height cloud properties. So if you want to know why you didn't see the surface when ICESat-2 went over your area, you can pull up ATL09 and get a picture of the atmospheric backscatter, which I'll show you an example of what that looks like. The disadvantages are this is a complicated product and it's not presented in the same along track coordinates as the along track products are. But it's extremely useful if you're interested in clouds or if you want to understand the atmospheric effects on some of the surface products. So this is a picture of what an ATL09 looks like. This is the backscatter. It's aggregated the number of photons coming back into histogram bins. And so it shows you some features like high clouds, clouds that are near the surface. You can see where the surface is here by an area of elevated backscatter right at the bottom of the plot. And you can see the varying noise levels as you look in different parts of the transect. So if I were looking someplace in Greenland and I wanted to know why I didn't see the surface, I could look at one of these ATL09s and see, oh, hey, there's a huge cloud layer there. Maybe it's not a big surprise that I didn't see the surface. So there are a lot of resources for learning more. The ICESat-2 webpage is a great place to start. It has links to the algorithm theoretical basis documents, which are the long documents that tell you too much about each of these products. You can get KMLs of the ground track locations, and you can get all sorts of fun stuff like Page the Penguin and the Photon and what they've been doing for the last year or so. The NSIDC landing pages are a great place to get distilled wisdom about each of the products. You get product formats, you can get known news on data releases, and you can get known issue descriptions. And you can also order the data themselves. So that's what I have for my talk. I'd be happy to take questions either in Slack or verbally. So I'll stop sharing my screen and see what people have had to say.